Dr. Maryna Nesterenko. She'll tell us about construction and application of quasicrystals. And could you share your screen?
Well, so first of all, let me to say thank you to all the team who organized this conference. It's nice to see all you here and to be a presenter. Today, I would like to tell about a bit unusual objects about quasicrystal, which now belong to such a part of geometry which is called discrete geometry. And I would like to tell how we can construct quasicrystals and propose you one modification for construction of quasicrystal, one new modification, and to propose you two practical applications of quasicrystals. To start with, let me tell you that quasicrystals are known in mathematics, not in a bit different names, but for a while. And the interest to quasicrystal was drawn by the paper of Daniel Shechtman and Blair when they were frozen some alloys. It was alloy of aluminum and magnesia, and I'm sorry, 1 moment. And they found that when they consider diffraction pattern of some local part, some spherical of the frozen this solid state material, that the diffraction pattern do not possess the condition of crystallography, because if you consider the symmetry angle, you can write it appropriately, but I hope you can see it something like, it's hard to write that when it online, because this angle is pi by 5. What is forbidden in crystallography? Because crystallography admits only axial symmetries of first, second, third, and fourth and sixth orders. After the discovery, a lot of materials were discovered that possess the same property. What does it mean? That we have some long-range order, but we don't have translational symmetry. So nowadays it is interesting to construct mathematical models for such an object. If we consider three-dimensional case, there are two possibilities. The first one, that in one dimension, we have translational symmetry, and in a plane, we have quasicrystal structure. And another possibility is that in all three-dimensional space, we have quasicrystal structure. So we have no translational symmetry in no dimension. So to construct such an object, up to now, there are several approaches. Let me explain you the basic ideas of this approach. On the right-hand side, you see the structure of real physical quasicrystal, and you can see that it consists of three key tiles. The first tile is square. The second one is equilateral triangle, and one more is a kind of diamond or like rhombus, such a shape. You can use to construct a big part of quasicrystal to study some physics, some potentials, or whatever on it, just by posing some tiling method. I mean that you should glue up edges of these tiles in some special way, for example, this one and then, and you can just make a program that will tile all the plane with such a small tiles. Next possibility is to try to divide existing tiles into the tiles of the same shape. I mean that you should divide squares into squares, triangles into triangles, and diamonds in such a way to the similar diamonds. In this way, you can get a bigger part of quasicrystal again and make some physics on it. But you see that this method is not keeps physical property, because it would be much better if you divide, for example, squares into triangles and into rhombus. and in squares into all types of parts, but only self-similar. And to do this is not so simple. It's not so easy problem to do it in such a way. And the last approach is scattered project method that I would like to show you in more details on the next page. Let us consider two-dimensional lattice, the standard square lattice. I mean points with integer coordinates on the plane. And let us consider two lines, straight lines, which are orthogonal each to other, and one of these lines will serve as our quasicrystal. And another one will be internal space, which is used to control construction of our crystals. What we do, we just project these points of a lattice with integer coefficients to our quasicrystal space, to our physical space. But we project not all the points, but only those points that are in some window in our internal space. In this way, we will obtain discrete set. And this discrete set will not have translational symmetry only in the case if this tangent of this angle will be irrational. That's the main requirement to construct one-dimensional quasicrystal from the square lattice. Actually, we can generalize this idea to multidimensional case and consider not only square lattices, but any lattice in space of twice higher dimensions that we need for our quasicrystal. So we can consider any lattice and make two projections. One projection is one-to-one, and another should be dense image. Then in one space, we choose some window, and if points fit to the window, then as another part of projection will give us the quasicrystal point. And the good choice for this lattice is lattices that have nice symmetries. For example, good choice is root lattices or weight lattices. This good choice. Why? Because we have a while group for symmetry of these lattices, and we can construct only part of quasicrystal and then apply reflections and get it in all space. So we can construct it only in while chamber. That's very convenient and give us good results. This is much more details. I will come back to these details. For example, if we would like to construct such a quasicrystal, which is physically interesting, we can apply root lattice of F4 group. And here are some details. I will skip them because they are not so essential now. And we can make projections and construct quasicrystal. But if you need points that are posed far from the beginning of the coordinates, you need to project more and more points because you don't know which of them will fit to the window. You see that there are many points are lost here. You need to study big amount of data and check it to understand which points will really give you quasicrystal point. To avoid this problem and to solve at the same time the problem of discretization of this fractal type of discretization of our tails, we can use another property. We can use the properties that root and weight lattices have not just Weyl group symmetry, but a fine Weyl group symmetry. And we can consider points not on the all Weyl chamber, but on fundamental domain. Here you see the dimension of fundamental domain. Then we have uniform way how to discretize it. And now we can project any big amount of points that we need and just flip our fundamental region and get points as far from the beginning of the our region of coordinates as far as we need. This approach gives us possibility to combine cut and project method and fractal method, and we get the way how we can discretize these cells of our quasicrystals, and at the same time we will get a much better result. Now I will show you my picture that I have. I'm sorry, I'm in another way. You see here we have problems, but if we use fundamental region and its discretization, everything is uniformly now, everything is nice. It's just beginning of coordinates, that's why pictures of such a form. But you can start fundamental region in any other place and everything will be the same. So that's the idea how we can improve construction of quasicrystals in general way. Now,
Maryna, may I ask the question?
Yes, of course.
The question: what are the assumptions on your crystal? How much it is symmetric? So, how do you choose this fundamental domain? What are the assumptions? So,
This fundamental, yes, these fundamental domains. You mean fundamental domains for the root system, or for what?
No, in general, I don't well understand.
Or you want to ask me about window? The exception window.
May I ask once again? So you have quasicrystal is something like let us look at this as like a tiling. Yes, this tiling, and it is on infinite plane.
Yes. It can be expanded everywhere. It's in RD. In fact, we start from R2D, and we project in two ways. Here we have acceptance window, and here we have this RD. Quasicrystal will be from one way, and this is finite for control.
But no, the question is, how do you know so is it symmetry? Maybe the group of symmetries of this tiling is trivial or not? What are the assumptions, the initial assumptions on your tiling?
We are constructing quasicrystals that we can see on diffraction pattern. We want to construct what physics give. We have rotational symmetry, for example. We see that we need to have 2 pi by 12, for example, divided by 12. So I look for root systems that possess this symmetry and try to project. My problem is to find this irrationality angle to project correctly to get the physical quasicrystal. But
Maryna, sorry, because I don't. Sorry, the question is: look, even in this picture, not at every point you have rotational symmetry. So the question is, what are actually the definition of your tiling and the group of symmetry of this tiling?
No. We have no group symmetry of this tiling. We have. Let me show you maybe more details. We ask only for symmetry comes from the lattice that we have. Some symmetry preserved under projection.
Yes.
My root system or my weight system have some symmetry. And when I project my lattice, root lattice, some symmetry preserved. That's the symmetry, but not all the symmetry, only part of it.
No, okay, thank you.
Probably maybe I don't understand your question, but
maybe let us if I ask you maybe later just
yes.
about it. Okay, thank you. Sorry.
So now I would like to tell you something about applications. Okay. So that's the construction of one-dimensional construction will be a bit later. Now, suppose that we have one-dimensional quasicrystal here, and we have some discrete data. We can make one-to-one correspondence to one-dimensional quasicrystal, and then we map quasicrystal points to acceptance window. They will be tossed in very complicated way. And after that, we can make one-to-one correspondence to discrete data again. of course, it's just shift transformation. It's not very interesting if we consider it, for example, like cipher or like cryptography coding. But this application is very useful when we would like to transfer some discrete data. Let me show you it on example. I have programs that makes it, but let me explain what happens there. For example, we have some image. I tested it on bitmap images. And on the image, we have some key information placed here. But when we transfer information, something can happen during our transition, and some part of data can be lost. For example, we lost this part. So we lost, for example, this logotype, which was on sale, which is important for us. But if we first use quasicrystal, here I use the same quasicrystal in both dimensional and only one-dimensional quasicrystal. Of course, we can use two-dimensional, we can expand data into one-dimensional row and so more. It will work much better. I just made it the same in both directions, just for example. And if we lost some information due to data transition at the same place and the same amount of information, and decode it, our lost information will be not contained in one place, but will be posted and on all the data, and these places will be periodic. You see here, they correspond to some special property of quasicrystals that I will show you on the next page. It spread only in one dimension because I used it only in one-dimensional quasicrystal. If I put it in one-dimensional, it will be spread not in lines, but in dots. In this example, I show you how it is spread in one dimension, this lost information. So it's very good for discrete data, because when you transfer it everywhere, and if you have some special important place that you don't want to lose, you will have about this about this logotype almost all information. Probably you can lose several points only. That's the first idea. Now I have not too much time, so probably I will not tell too much about practical construction of quasicrystal. Just let me to say that it's convenient to work with irrationalities that not transcendental. It's better to take such irrationalities that are connected by some quadratic equations, because it's very convenient. Then all calculations are made in integer numbers. So all one-dimensional quasicrystals will be described by this family or this family of quadratic equations, and they have some nice properties. One of important properties that distances between two neighbor or two adjacent points will be only of three types: D1, D2, and their sum. But it depends on the relation between distance and acceptance window, and size of acceptance window. In some cases, we can construct such a quasicrystal that will have only two different points in one-dimensional, two different distances between adjacent points in one-dimensional quasicrystal. And this property allows us construct keys for Vernam cipher. I will skip these details, how it's constructed, and so on. This one, you see, I shown you example of the quasicrystal of only two distances. One of these distances can be considered as true and one of the as a false. And then we can construct a key of any length for a Vernam cipher. And using this XOR operation, which is key in Vernam cipher, we can skip this one and this one. We don't need this plain text anymore. We can just encode binary code of any data using this quasicrystal one-dimensional. And here you can see what type of crypto variables we can get, and Let me mention that Vernam cipher is a stable cipher, one of not a big amount of stable ciphers. And these crypto variables are very simple, and it's enough if you need to transfer a private key. The smallest necessary information is 2 integer numbers for seed point and 1 integer number for the quadratic equation. This is the smallest information that make your information safe. It's very small amount that can be used. That's all what I would like to say for now. Probably you have some questions and I can give you some more details.
Thank you very much for the presentation.